natural numbers to the topological space. Right. And this is the definition. Sequence converges to a point P in X if for any neighborhood, what is a neighborhood?
Set that contains an open set that contains that point.
Okay, so it's a possibly not open set which contains an open set, right? So neighborhoods can be yucky, right? Not my neighborhood, though. I like my neighborhood. For any neighborhood U of P, there exists N in N such that A sub N is an element of U for all N greater than or equal to N. Let's see here. So if this is the space X, right? And if this is the point P, right? And basically, I got sequence. You know, if for any neighborhood U of P, maybe the neighborhood U looks like that. I don't know, whatever. And then what does the sequence look like? Well, the sequence is harder to draw, but could be okay, you get the idea. So if this, you know, right here is like n equals to, I don't know, 30, maybe that would work for my particular choice of U. Right? The point is, for any neighborhood you pick, you can pick an n big enough so that the sequence, no matter how weirdly it's behaving, right, you can get the rest of the sequence inside the open set. This does not imply P is unique. It's messed up, isn't it? So here, it's 1. So the convergence of a sequence need not be unique. Now, you should ask me for an example of that, and I can't give you one yet. Okay, a point P is called the limit point. What does that mean? Of the sequence. If for any neighborhood U of P and for every n in the natural numbers, what do we need? Big N, the natural numbers. There exists n greater than or equal to n such that A sub n is an element of U. P is a limit point of sequence if for any neighborhood U of P and for every n in the natural numbers. We can find some little n in the natural numbers beyond n such that an is in U. It doesn't say that all of the little n have to be in U, but there have to be some.
It's like -1 to the n when we get that sequence. got 2 limit points.
Right.
This is for any natural number you choose. You can always choose like one that's even bigger than it, and that will be within.
Right, so, yeah. Should have 2 convergent sequences, put in the odd and put in the even, and you have one going to one thing, one going to the other thing. You've experienced it in Reals already, right?
I'm not in real.
You're not in Reals?
No.
Oh. I'm sorry. Oh, that's Neji Hoogerwerf, right?
Yeah.
Yeah, okay.
Neji.
Yeah, that's,
Neji.
I need to write some problems for Neji here. Yeah, they never brought him back. Oh, sorry, spoiler alert. But he dies and he never comes back.
I did find that out from my friend who actually watches it.
Yeah.
I'm curious.
Goodness gracious. He says, saying a sequence accumulates at P means that P is the limit point. If a sequence converges to P, then it also accumulates to P. So P is the limit point, and the converse is generally false. Converse is what?
If it's a limit point, then it converges.
Right, because like you said, the plus minus 1 sequence has 2 accumulation points, 1 and minus 1, but it doesn't converge to either. Every sequence in a Hausdorff space converges to at most 1 point, if it converges at all. Because if you had a sequence which converged to distinct points P and Q, let's go through this argument. It's probably worth going through. I mean, I have a more general question, and so oh, he hasn't. Could we define limit here somewhere? Like limit as n goes to infinity of no. Did we define like limit as x goes to a of f of x equals to L somewhere before? Did we ever define that?
I don't believe so
Not that I
either.
can remember.
I don't think we did. I mean, of course you could define, you could say the limit as n goes to infinity of a sub n equals to p, given this condition, right?
I think in the next definition he defines limit.
Oh, he does? Okay.
Yeah.
Let me hold off then on my jibber jabber. So if you had a Hausdorff space, right? Hausdorff X, and suppose you had a sub n going to P and also going to Q with P not equal to Q, what would that look like? So that would mean there are disjoint neighborhoods, right? Well, there exists U and V, disjoint, right? With what? P an element of U, and Q an element of V, right? And then the thing is what?
It's 5:00 p.m.
Shut up. I hate you. Sorry. And it says, and integers n and m. I can almost see it, but I can't quite say it yet. Such that what?
For all n greater than
And is an element of U, right? For all n greater than or equal to n. And
is
an
not going to be.
element of V. For all n greater than or equal to m. So,
if you take the max of the two, then it's going to be two disjoint sets.
The k equals the max of nm, then you have what? an is an element of u, and an is an element of v for all n greater than k, which is very troubling, since they're, yeah, that's not happy. Consequently, impossible. So in a Hausdorff space, by contradiction, the limit is in fact unique. And so his definition, he assumes Hausdorff for the definition, right? A sequence, and I'm not sure that's necessary. A sequence, A sub n, I mean, it's convenient, but there are these kinds of, I showed up, said to be convergent. If it converges, okay, thanks, to P and X, yeah, okay, shocking terminology there. When X Hausdorff, this Hausdorff, you also say that P is the limit of A sub n is the, as in singular, limit of the sequence A sub n, and we write, that is, A sub n is going to P, or the limit as n goes to infinity of A sub n is equal to P. All right. Let me tell you about where we're going. So the next move here is to define subsequence, right? And then he has the lemma that if a sequence, if you have a sequence in X, if there's a subsequence converging to P, then P is a limit point for A. For example, the subsequence of constant 1 or -1 in Daniel's example. Then what? Then we have a first countable space, A a subset. Following our equivalent, there exists a sequence of values in A that converges to X. The point X is a limit point of an A-valued sequence. The point X belongs to the closure of A. Right, so limit points are, what is the word? I mean, it depends on how you couch things in reals, I don't remember. But so we get this connection between limit points and the closure, right? In a compact space, any sequence has limit points. In other words, topological compactness implies sequential compactness. Definition: a space X is sequentially compact if every sequence has a convergent subsequence. Okay, so that's sequential compactness. Every convergent sequence having a convergent subsequence. That's how we measure compactness using sequences. But that's not a general notion of compactness. Like, sequences are not enough to measure general topological ideas. They're too limited. That was accidental. Sorry about that. I don't retract it though.
That's what they're called, limits.
Yeah. Sorry. Following our equivalent in a second countable space X. X is compact. Every sequence in X has a limit point. X is sequentially compact. Yeah. Okay. So I think a lot of this really is just honest to goodness real analysis. I mean, you've seen a lot of this in reals this semester, I think. Or you will soon. But anyway, I might come back to that next time, I'm not sure now. Next he talks about Cauchy sequences and completeness. Some of that we've talked about before other places. And then he talks about compact metric spaces. Bayer's theorem, about meager, nowhere dense sets and such. What is a bare space? The big theorem: complete metric spaces and locally compact Hausdorff spaces are bare spaces, whatever that means. And then there's a section on completions that we could skip, but I probably won't because I actually think that one's interesting. For example, the completion, right? You could take the rational numbers and do something called the completion to it, and you know what happens when you get out? What comes out?
Real numbers.
Real numbers, right? If you take the rational numbers and you complete them with respect to a different metric than the Euclidean one, you get something else, though, I think.
P at X, right?
Yeah, I was hoping you'd have a homework problem. He does something with the ring of polynomials over a field K and going something about the formal power series. Then 6.7 is on function spaces and Ascoli Arzella? I don't know how to say that. I'm mispronouncing that horribly. Probably will. I have to decide whether or not there's anything in there worth trying to verbalize Friday there. 6.8 is interesting. It's on directed sets and nets. So the thing that replaces sequences in topology is the notion of a net. A net is a generalized sequence, basically. And where sequences break down, nets don't. And nets can be, nets do capture topology pretty generally. It's beyond that, there's things called filters and ultrafilters, which are logically beautiful, but are, let's say, harder to make intuitive. Logically, they're just very, very beautiful, pure nonsense. Not nonsense. It's one of the things the Bourbaki brought to us and left with us, and most of us are still trying to understand. But people who are honest to goodness topologists, it's bread, it's butter, it's not a big deal. But anyway, so I'll try to talk about nets. I'm hoping I spend a good bit of our time Friday on nets. In particular, what I'd like to do is find an example where the notion of sequence is not enough to capture the idea of convergence, whereas net is. That would be what I'd like to do. And at that point, that's kind of it for this book. I mean, he's got this chapter on topological manifolds and stuff, but I probably can get more out of something else. Oh, ultrafilters is 8.4, and there are doubtless things that we could cover. But I think I'm probably going to change gears after break, and so we'll try to finish the nets here, and I'll try to create a test for you guys on this book, or maybe a subset of this book, and then we'll do another subset. I'll have to think about the test, right? Well, I will think about that, and hopefully I will actually grade your homework. There's that. And more importantly, I will show you next time, if I don't forget, and I better not forget because this is important, I will show you the most hilarious handout my brother ever gave in any class. And it's all about it's really in the next chapter beyond the classification axioms, T1 versus T2 versus T3 versus T4. And that actually goes back to your question, like, can you find an account? It's this kind of thing, like this demarcation of spaces into different types, and do you really need Hausdorff? There was a period of time where we tried to build Hausdorff into the actual definition of topology. It's that important. I mean, there are that many examples which need Hausdorff. It may almost make sense to build it into the definition.
It would be easier to just include it than to just differentiate it between those that are not.
Right, in some sense, but then on the other hand, there are important examples of function spaces which aren't Hausdorff. So it didn't make the cut in the end, even though it is, of course, if you want maximal intuitiveness, yeah. But if you want maximal logical flexibility, that's, I think, the resting point of the definition. That's why it is what it is. Anyway.
So we're pretty much like done after chapter 6, you're saying?
Yep. I think Friday we should wrap up what I have to say about the book. And then, of course, we're not really done because we need to work some collection of homework problems and You know, we can still talk about it. It's
Yeah.
fine. I'm not saying that. What I want to do though is I want to move on and show you guys some interesting things, some things that I didn't do in complex and didn't do in advanced calculus, but are important. For example, I want to take a week and I want to prove the contraction mapping principle. I want to prove for you, if things go well, I'd like to prove the existence and uniqueness theorem for ODEs. Some like deeper analysis results that you just won't see in
I
coursework.
like that. I really appreciated the differential equation side of that. Going further into depth, 334 stuff.
Yeah,
I like that.
I have my own selfish reasons for also looking at the existence and uniqueness theorem for DPQ.
What's that?
Well, I want to see if I can generalize it from the real vector space to another thing.
Hmm.
I want to see if I can make sense of it for algebra differential equations. Once that's done, I probably will transition over in here to manifolds. And I'll try to do some basic manifold theory with you guys. For serious this time though.
For serious.
Yeah.
For reals.
For reals. And you can turn it off, this is the secret